Hello everyone, and welcome back to another remote sensing lecture video. And in this video, I want to delve a little bit deeper into this idea of electromagnetic radiation and the electromagnetic spectrum. Specifically, I want to address the question, where does electromagnetic radiation come from? So, to address this question, what we need to know are a couple of things, and a couple of equations specifically. These aren't equations that I would necessarily expect a introductory student to perform, but more so just to understand the relationships between the different components. And so the first equation that I want to discuss is the equation that relates the total amount of energy produced to temperature. So we're going to be talking about this idea of electromagnetic radiation as a function of temperature. Right, electromagnetic radiation as a function of temperature. And there's really two equations that we need to sort of be aware of. Again, I wouldn't necessarily expect you to calculate them, but again, just be aware of their structure and what that structure means for the relationships. So first is going to be the total energy produced. Let's make that a little bit cleaner here. Total energy produced. And we're going to use a symbol here called M with a little subscript lambda here. I'm trying to make sure I get this drawn accurately with a total little subscript lambda. That's not really a subscript. Let's try to make that a little smaller here. With a subscript lambda like so. That's the total energy produced. So we have M subscript lambda is equal to, and then you'll see this symbol in most of the times when you see this equation, you'll see this symbol here, and then you'll see a t to the fourth power. This right here, this is the Stefan-Boltzmann constant. Stefan-Boltzmann constant. And if you're interested, it is approximately 5.6697 times 10 to the negative 8th watts per meter squared per temperature, or Kelvin, to the negative 4. So this T here, right, this is the temperature measured in kelvins. In Kelvin. Right, so what this is saying here, again, I wouldn't expect you to calculate this, but what this is saying here is that the hotter the object, right, at a very high pace, the hotter the object, the more energy is produced. So again, the hotter the object, the more energy is produced. That's one thing we can do. Another thing that might be interesting is to figure out, well, what is the maximum wavelength, or what wavelength is predominantly emitted? Oop, make that a little bit cleaner. What is the predominant wavelength? And so we call this predominant wavelength. We again use lambda here, and we put a subscript max. Right? What is lambda max? And so lambda max here is going to be equal to K. Let's make that look a little bit cleaner. It's going to be equal to K over T, where T is again temperature measured in Kelvin. Right, temperature measured in Kelvin. And this K right here, this is another constant. And this constant has a value of, in case you're curious, 2,898 micrometer, so Kelvin. Micrometer Kelvin. So if you do the math here, right, based on just the units, temperatures in Kelvin, the constants in micrometer Kelvin, the Kelvins cancel out and you're left with micrometers for the maximum wavelength. So what does this equation tell us? Actually, no, let's go ahead and let's actually write down our findings here. So what this equation tells us, right, going back up here for just a second, what this equation told us, right, was that hotter objects produce more energy. Let's clean that up just a little bit. Hotter objects produce more energy. What does this equation tell us? Well, we have lambda max, which is the predominant wavelength. We have this constant that's some constant of micrometers Kelvin divided by the temperature measured in Kelvin. So this top part here, this is a constant, right? This is never going to change regardless of what we do. I mean, obviously, we could change it if we change the units, but this number here is never going to change regardless of what this equation does. So what we have is a constant divided by some number that's changing. So as the temperature here increases, right, as the object gets hotter, right, the denominator here gets bigger, while the numerator stays the same. And when that happens, this whole number decreases. So as you decrease the left-hand side here, or decrease the right-hand side here, sorry, the left-hand side decreases, which means our lambda max is shorter, or is smaller, which means shorter wavelength. So what this means here is that as your temperature increases, your wavelength gets shorter. So to put that in here, right, hotter objects produce shorter wavelengths. Right? Hotter objects produce shorter wavelengths. So again, hopefully this made sense. I know there's kind of a little bit of math here. If you don't understand part of it, I encourage you to pause the video, go back, rewatch the parts you're confused about, And as always, please reach out. Thank you.